Okay, here is a derivation of the energy density in an electric field. Let's start with a capacitor. Okay, so this capacitor, if you remember, if you have two plates close together, then if you just have, it makes a constant electric field. If you just have one plate, the electric field due to one plate, called EP, the magnitude, would be, let's see, it's Q over A over epsilon naught, and the 2's on the bottom or the top? I don't know, I always forget that. It's on the bottom. So it doesn't depend on the separation. So that's important, because if you pull them apart, you still get the same electric field if you have the same charge in the same area. So this exerts a force on that, because this makes an electric field. This is the electric field due to one of them, and that's a charge. So what's the force on that plate? There's a force that way, F. And since it's a constant electric field, then I can just say F equals, well, you can say, and if you break, this is like a whole bunch of little point charges, they all have the same force on them because it's a constant electric field. That's what I was trying to say. Q of that plate times the electric field of this plate. So you get Q squared over A over 2 epsilon naught. That's the force on that other plate. Okay, now what if I then take those plates and I pull it apart a little bit? Well, if there's a force on it, then I'm going to have to push on it that way to get it to go apart. And so I'm going to have to do work. So the work is going to be the change in potential energy in that case. I'm going to make it have a higher energy by putting work into it. Putting work into it is a terrible thing to say, and I apologize. I shouldn't have said it. By doing work. Okay, so that would just be, let's say this moves over delta S, and then this is going to be F delta S. That's going to be the work done. And that's going to be the change in energy. So I can write the change in potential energy as F, which is going to be Q squared delta S over 2 epsilon naught A. Okay, so I have more energy in this, and this is a constant electric field inside there. What if I want, let's just go ahead and find the change in volume. If I increase the energy by a certain volume, then that change in energy divided by the change in volume is the energy density for that new area. So I have delta U over delta V, the volume, is going to be Q squared over delta S over 2 epsilon naught A. Now to divide this side by the volume of this new piece over here, if I pull it apart, it's going to be the area of this times how far I pulled it apart. That's going to be the new volume. So it's just going to be A delta S. That's the volume. Okay, so now I get these cancel. And I get 1/2 Q squared over epsilon naught A squared. And I can write that as 1/2 epsilon naught Q over A over epsilon naught squared. That's the same thing, right? Right? Right. It is. If you square that, you get that. The epsilon naughts cancel. This is the electric field due to a parallel plate capacitor. Okay? So this is just going to be the electric field inside, so I get 1/2 the magnitude E squared. So that is the energy field, the electric field energy density. That's the energy per unit volume in a region with electric field. There is energy stored in the electric field, and that's how much.